welcome to Sanford Flip Math. This is Algebra 2. We are working our way through the SpringBoard Algebra 2 book, although this content could relate to any Algebra 2 book or even some pre-calc books. What we're talking about is transformations. Transformation is the overall category, and basically what we're going to do is specifically talk about transformations on functions or equations or graphs. Could apply to geometric type issues, but we're focusing on specifically on equations and what happens to their graphs when we do that. So transformation is the overall category. This particular video is going to focus on translations and probably reflections a little bit depending on time, but we'll see how that goes. Okay, so the big focus for us right now will be on translations, and I need to remind you that all of this is going to be in reference to a parent function. Okay, so parent functions, as we've talked about already in class, they're the simplest version of a function that has that function's characteristics. So for instance, if I have an equation that looks like something like this, then really this is about the parent function is absolute value of x. So you already know, just by knowing what you know about absolute value of x, it's going to be a V shape. This thing will be a V shape also. Now what we need to do is, our focus in this video is going to be, okay, what do you do about x plus 3 and the minus 1? How does that affect things? And then the next video will be what happens with that 3 on the outside. So really it's going to be about what happens. So you need to have a picture in your brain before we even start of what this graph is going to look like. Okay, so and a lot of this is about how do we predict what's happening. So a translation is a move, a slide, a shift of some kind of a shape or graphs. Now again, we're focusing specifically on graphs in this video, okay, and in this course. Okay, so I'm going to do a lot of work with y equals x squared today on this video, and then we'll work in others here and there. Okay, so I need you to have a pretty good handle on what the graph of y equals x squared looks like, and I'm going to typically be working from these 5 points for the parent function, and negative 2 squared is 4, negative 1 squared is 1, 0, 1, 4. Okay, so all I'm doing is graphing these points, and I'm not going to graph them like this every single time because we're going to be looking at this a lot. Okay, so here is the parent function y equals x squared. Okay, and just for other reference, here is the parent function y equals x squared. Okay, and I'm going to do what the calculator calls a zoom decimal screen, and all that does is it lets, if I do tracing on the screen on the graph, then it'll actually have nice numbers. Now if you're using a standard TI-84, the numbers might come out just a tiny bit different because the TI-84 color actually has a little tighter dot per inch kind of thing. The pixels are smaller. So don't freak out. You can just do zoom decimal on your calculator, whether it's a 82, 83, 84, or 84 color, and it'll look pretty similar. Okay, so this is what y equals x squared looks like. This is what y equals x squared looks like. Okay, so now the question is, what if I do y equals x squared minus 3? Okay, so again, I'm not going to do points every time like this, but I'm going to do it now just because we're getting started. Okay, so I'm just substituting in negative 2 squared. Now remember, negative 2 squared is really 4. You have to be careful how you write things down. 4 minus 3 is 1. 2 squared is 4 minus 3 is 1. Okay, if I put negative 1 in, negative 1 squared is 1, minus 3 is negative 2. And if I put positive in, I also get negative 2. And put 0 in, 0 squared minus 3 is negative 3. Okay, I'm going to graph this on the same axes. And here are those points from the table. Okay. and I want to just kind of key in on a couple of issues here. Remember, this is not a line, so the slope is not the same everywhere I look. But notice how if I go right 1, I go up 1 on this. I'm on the blue graph. If I go right 2, I go up 4. If I go left 1, I go up 1. If I go left 2, I go up 4. That's that whole idea of the 1 squared and 2 squared. Well, the same is true on the red graph. If I go right 1, I'm going up 1. If I go right 2, I'm going up 4. That pattern for x squared might be helpful to you so that you don't have to put in so many points. So it's like 1 is 1 and 2 is 4. Okay, unless there's some kind of other stretch or shrink going on, and that's really the next video. Okay, I want to pop over to the graph, the calculator, x squared minus 3. Okay, so we're going to type that in, x squared minus 3. And here it comes. Now I know that the graphing calculator the red graph appears to be bigger, but I'm here to tell you it's really not bigger. If I had a way to measure this, and I don't think I have a way to show you this on here, like where it'll show up on the screen, but if I had a way to measure across, like right here, and then measure across in that same spot, this distance, well, I do have a way I can count. That distance is 2, this distance is still 2, okay, because of the way that lines up, okay? The red graph really isn't any bigger. The red graph is just shifted down, and because it's shifted down, it actually appears to be bigger, okay? So it's not really bigger, it's just appearing to be bigger because you're seeing more of it. Remember that these graphs go up forever. Okay, so the blue graph goes up forever, the red graph goes up forever, so there is no height. It's not like one is bigger than the other, okay? All right, so the big message for this is, where did the graph go? Well, it looks to me like it went down 3. If I pop back over to the other graph that I did by hand, it looks to me like this graph shifted down 3. So what I need you to see is when this 3 was on the outside, so I had y equals x squared, I had y equals x squared minus 3, and what happened? This minus 3 made the graph go down 3, so down 3 on the graph. Okay, so that's a big deal. Okay, so I guess the question ought to be, what happens if I do something different? Okay, let me make the ink go away. Okay, so I'm going to go down, I'm going to change this. So I'm going to do x squared. Now you can just type over the top of stuff. What if I do plus 1? What do you think is really going to happen to that graph? So again, we are always comparing to the parent function. Okay, so this guy right here is the parent function. This would be the parent function, but there's this plus 1 on it. How does x squared plus 1 compare to the parent function? Okay, so let's hit graph. Here comes the parent function. Here comes x squared plus 1. Plus 1. Is it where you thought it would be? Do you see where it's going? I feel like Dora, you know. So, did you like this one or that one? Okay, so did the new graph appear where you expected it to appear? With a plus 1, it went up 1. Okay, so quick little note here. Addition or subtraction on the outside of the graph, or on the outside of the function. So like this minus 3 was outside the x squared, not x minus 3 squared. On the outside of the function, moves, shifts, slides the graph up or down. Okay, so if it's plus, it's up. If it's minus, it's down. Okay, all right, so now I want to play with your brain a little bit, and I'm not trying to be mean, but I have to do it. Sorry. All right, so I have x squared as my parent function. This time I'm going to do x minus 3 inside parentheses. Okay, so x minus 3. Now, before I reveal what happens, I need you to think, where do you expect it to go? Okay, so when we did x squared minus 3, and the minus 3 was on the outside, it went down. X minus 3 on the inside, that minus 3. So see how this is inside the squaring? Okay, that's a big deal. Okay, now we're going to see, where does this graph go now? Okay, so I'm going to push graph. Think about where you think it's going to go. Here's the parent function. Here's x squared minus 3. Or x minus 3 squared, sorry. Whoa, did it go where you thought it would? So remember that the equation that we graphed, the red one, was x squared minus 3. And when we graphed it, it actually went right 3. Okay, so what the heck is going on? That is shocking. Shocking. To me, it's shocking. Anyway, maybe it's not to you. Maybe you already know this stuff. That's awesome if you do. So a minus 3 made it go right 3. A minus 3 made it go right 3. Okay, let's go and do kind of like what we did before. We did x squared plus 1. Well, I'm going to do x just plus 1. Okay, notice that this is on the inside now. Okay. So where do you think it's going to go with the new information you had before? So the vertex of the parent function is at 0, 0. So notice this time it went left 1. Left 1. Okay, let me make that go away. Thank you. All right, so again, we are on x plus 1, and it went left 1. Now, to me, that seems counterintuitive. I expect things, you know, when I see plus 1, I expect things to go to the right or up. But it feels backwards to me, but that's just because of it being on the inside. Okay, so let's make some notes about this. Okay, so again, we had y equals x squared. When we did y equals x minus 3 squared, it went right. That was a weird, I started to write an L, sorry. It went right 3. When we did y equals x plus 1 squared, it went left 3. Okay, so here's the big deal, big takeaway on this. Addition or subtraction on the inside of a function, like inside squaring of an equation, I'll say, moves the graph left or right. Big note here. But the inside, you have to do the inverse. So if you see plus something on the inside, it really goes in the negative direction. If you see minus something on the inside, it really goes in the positive direction. Now, I know some of you are going to want to say opposite, and that's okay, but I'd rather you say inverse. And the reason I want you to say inverse is because the next section, or the next part of this that we do, is going to be about multiplication and division, and it's not going to be opposite, it's going to be inverse. The inverse of multiplication is division, the inverse of division is multiplication, and the rules still apply. Okay, so quick recap of what we've done. Addition or subtraction on the outside moves it up or down, and you do what it says. Okay, so in other words, if it's positive, you go up. If it's negative, go down. Okay, addition or subtraction, if it's positive, go up, negative, go down, if it's on the outside. So on the outside, you do what it says. On the inside, you do the inverse. Inside, you do the inverse. Big deal, huge deal, very important. Yeah, the reflection thing is not going to happen on this video, but that's okay. We'll catch it with the next video. Okay, I want to do one other thing here, and let's do absolute value. Okay, I'm going to change the parent function to an absolute value function. If you are working on a new system, some TI-84s have the new system on them. Some TI-84s do not. Okay, so let me show you what I just did. I'm being sneaky. I'm going to go to y equals, okay, and there are some shortcuts, and some of your phones have what are called soft keys. Well, on the TI-84 in the new system or the TI-84C, if you push alpha, the top row becomes soft keys. So I'm going to push window now. Okay, so I'm pushing window, and notice how I get like this whole extra little menu kind of thing that showed up here. So this came from pushing. I did alpha, and then I pushed the window key. And you can play around with this, but it's kind of sweet. Okay, and then the reason I did that is because I want to do absolute value. So now I can push 1, and there's absolute value of x. Okay, and now you already know that that looks like a V shape. It has its corner at 0, 0. This is the parent function for absolute value. Okay, so what we're going to do is 3 quick little graphs, and all we want to do is try and predict where they're going to go. Okay, excuse me. All right, so I'm going to do alpha window again so I can get absolute value. And I'm doing x. Whoop. Now what happened there? I'm not supposed to do that. Sorry. Okay, so x, there it is. And then I want to do, let's do -5. So x squared minus 5, or I'm sorry, absolute value of x minus 5. And I want you to, before you look ahead, I want you to think, where do you think the graph went? Did it go there? Holy cows, Mr. Sanford, I can't even see the bottom. All right, well, let's play with the window a little bit. How far down do I need to go? Now, down is a y value, so I'm going to go down to -10. I probably should have just done zoom, whatever that zoom is, zoom standard. Sorry. All right, so here it is. Now, it looks a little squished, but that's because the window is distorted because I changed the y's without changing the x's. Does that make sense? Remember what the equation was. Absolute value of x minus 5. Look how far down we went. Oh, it looks like 5. I think that's kind of sweet. Okay. Again, we have minus 5 on the outside. Outside means it's going to talk about something about being up or down. It's about y. And you do what it says. Not inverse. Well, it says minus 5, so intuitively, I think that means 5 down. Okay, and that's right. Okay. Okay, let's change it up a little bit. Okay, I want to do, let's do -5 again, but I'm getting rid of the stuff on the outside. Okay, now this time, notice where the x minus 5 is. So it's on the, is it inside or outside? Inside. Does that mean it moves up and down or side to side? It's going to be side to side because when it's inside, it's about x with a variable it's with. Okay, so it's inside, which means it's with x, which means it's horizontal, which means left or right. And remember, it's inverse. So I think it's going to go right 5. That's what I think. Okay, so let's see what happens. Still working with that funky window we had. Here it comes. Looks like right 5 to me. I'm going to do zoom, and I'm going to do standard, which is 6. And this makes it go to the, not that far. Come on, where are you going? There we go. 6, zoom standard. That makes the normal -10 to 10 screen that most people are used to seeing. Okay, and then I'm going to pop back, and we're going to do one more, and then we'll be done. Okay, again, all we're trying to do right now is predict where things are going. Okay, so I'm going to make this, let's do +2, and then, it's going to do more, -3. So x plus 2 minus 3. Now, I want you to think about where do you think this is going to go, because there are 2 different things happening. Okay, so think about where what this is going to do, and think about what this is going to do. Hit pause and sketch it. I want you to hit pause and sketch it before you see what that graph actually does. Okay, now I hope you already did that. Okay, so this is going to, I'm thinking it's going to go down 3. because outside you do what it says and it's about up or down. Inside you do inverse and it's about left or right. So I think it's going to go left 2. Okay, so I would say move, I would say slide, I would say translate, I would say shift, I would see any of those. Okay, now let's see if that, so left 2, down 3. Let's see the graph. Okay, so there's the parent function. Does it move left 2 and down 3? Okay, so left 2, oh, wrong color, sorry. Left 2, 1, 2, and down 3, 1, 2. Now, really, it's every single point on this graph that's moving. I'm just keying in on probably what I consider the most important point, which is the vertex, that corner, because it's easy to spot. Really, all of these points are moving left 2 and down 3. So like this point over here, whatever that was, 3, 3, I guess, it moved left 2 and down 3. Oh, sorry, down 3. Left 2, down 3. Because all of these points are moving. All right, so this whole video was about translations, slides. It's all about addition or subtraction. One last time, remember if it's adding or subtracting on the inside, it's left or right, it's in the X direction, it's inverse, inside, inverse, inside, inverse. You'll hear me say that a million times. If it's adding or subtracting on the outside, it moves up or down with Y, and you just do what it says. That's the easy one. Okay. All right, thanks for watching Sanford Flip Math. We will be together again. Bye.